Okay, so so far we know that a Mobius transformation S is a map from C infinity to C infinity. Okay, and that is determined uniquely. Determined uniquely by three different points. Okay, so now let's try to make this concrete and see how we determine a Mobius transformation. Okay. Okay, so three different points. Let Z2, Z3, and Z4 be different points. In C infinity. Okay, and then we define a Mobius transformation. Define S from C infinity to C infinity by the following. So there are four cases. Case 1, if all of them are non-infinity. So case 1, Z2, Z3, Z4 are all in C. In this case, our S is defined to be Z minus Z3 over Z minus Z4 and divided by Z2 minus Z3 over Z2 minus Z4. Okay? So first you use Z minus Z3, Z minus Z4, and divide by Z2 minus Z3 and Z2 minus Z4. So we can see that if we have Z2 here, S of Z2, the numerator is Z2 minus Z3, Z2 minus Z4. Denominator, same thing. So S of Z2 is 1. S of Z3, you let Z be Z3, the numerator becomes 0. It is 0. And S of Z4, you have 0 denominator, non-zero numerator. It's infinity. Okay? So this is the property we want. For those three different points, if they are all complex numbers, then we want a Mobius transformation so that they map the first point to 1, second point to 0, and third point to infinity. 1, 0, infinity. Okay? This is like actually the aim. Okay, so now let's see what happens if Z2 is infinity. Because our Z2, Z3, Z4 are different points in C infinity. One of them could be infinity. If Z2 is infinity, let's see, Z2 is infinity. This denominator actually has a ratio 1. Z2 is infinity. This denominator has a ratio, the limit is 1. So we will just have such form expression, or just have this. And this Mobius transformation also satisfies the condition. Okay? You check the limit, this S also satisfies the requirement. And what happens if Z3 is infinity? If Z3 is infinity, we are going to see here, this Z3, they are both numerator of the top and bottom. They actually cancelled. So you will just have Z2 minus Z4 and Z minus Z4. Okay? So you cancel this numerator and flip this denominator to the numerator. So you get a Z2 minus Z4 and a Z minus Z4. And you check that when Z2 is 1, when Z is Z3, it's 0 because you have an infinity denominator. When Z is E4, we have infinity. The same property, same property. This property is always kept in our definition. And third one, the fourth one, if Z4 is infinity, we cancel the denominator. We will have Z minus Z3 over Z2 minus Z3. Z minus Z3 over Z2 minus Z3. And you check that this also satisfies the condition. Okay, so S is the, because you see here we have three different points and we name them to three different values, and it will uniquely determine a Mobius transformation. So S is the unique Mobius transformation satisfying S of Z2 equal to 1, S of Z3 equal to 0, S of Z4 equal to infinity. Okay, so that's the construction of the unique Mobius transformation with the given property. Okay, and this construction is based on this fixed point property of the Mobius transformation, if it's not an identity map. Okay, so next let's see a commonly used notation definition. If Z1 is a point in the C infinity, then this symbol Z1, Z2, Z3, Z4 is called the cross ratio. The cross ratio of Z1, Z2, Z3, Z4 is the image of Z1 under the unique Mobius transformation which takes Z2 to 1, Z3 to 0, and Z4 to infinity. Okay, that's an image. It's an image. So what is this definition? It's actually the following value. So if, for example, if Z2, Z3, Z4 are all in C, then this symbol cross ratio of those four numbers is actually just the Z1 minus Z3 over Z1 minus Z4 over Z2 minus Z3, Z2 minus Z4. It's just this complex ratio. Okay, composite ratio. It's nothing else. If there, we just actually apply the first formula to the evaluation. It's an image. Image is this evaluation, right? And we also see that because of this requirement, the Mobius transformation will satisfy those three conditions. We can see that the cross ratio Z2, Z2, Z3, Z4, it should be 1, right? It maps Z2 to 1. So once this first term is Z2, it will be 1. And the first point is if z3, it's going to be 0. If the first point is z4, it should be infinity. Just repeat those conditions. And any Mobius transformation, if M is a Mobius transformation with mz2 to be 1, mz3 to be 0, mz4 to be infinity. If M is such transformation, then M, because the transformation with those property is unique, then M of Z must be this cross ratio. The cross ratio is unique words here, this word, the unique, right? It must be unique. Okay, so far, keep this construction in mind because we will frequently recall it. And this cross ratio just has a property, maps the second number to 1, third number to 0, and the fourth number to infinity. 1, 0, infinity. 1, 0, infinity. It goes this way, opposite way of a positive direction. So 1, 0, infinity. Z2, Z3, and Z4. Z2 maps to 1, Z3 maps to 0, Z4 maps to infinity. Okay, it goes to the negative direction. All right. Okay, now let's see the property of such cross ratio. This cross ratio has a lot of interesting properties. Let's see the property. First of all, cross ratio is a Mobius transformation. Is a Mobius transformation. Let's see what is the composition between the cross ratio and other Mobius transformation. So if Z2, Z3, Z4 are distinct points, and T is any Mobius transformation, arbitrary Mobius transformation, then it says Z1, Z2, Z3, Z4 cross ratio is equal to T of a Z1, T of a Z2, T of a Z3, and T of a Z4 for any point Z1. So if you apply arbitrary Mobius transformation to this those 4 points, you do not change the cross ratio. So that's what this theorem means. Well, actually, frankly speaking, we can actually compute it solidly by the definition, like T. What is a T? T is a AZ plus B over CZ plus D. You can do the computation and eventually you see, okay, the right side is equal to the left side. No problem. But now let's try to use symbols and the properties to prove it. Okay? So this is a Mobius transformation. So let S of Z be Z, Z2, Z3, Z4. So this is a one Mobius transformation. Be the Mobius transformation. Okay. Then let's check define another Mobius transformation F to be S composed with T inverse. T is a Mobius transformation. T inverse is also a Mobius transformation. Remember, what is a T inverse? T inverse of Z. You change C and D. You change exchange A and D. Change the sign of B and C. Exchange A and D. Change the sign of B and C. Okay, so this is T inverse. We compose the Mobius transformation with a T inverse. Then we define it, call it M. We call it M. Now let's see. For this new Mobius transformation, let's check TMZ2. MTZ2. MTZ2 is S T inverse TZ2. Right? So it is actually S of Z2. S of Z2 is 1. S of Z2 is equal to 1. It's by the definition here. And then M of TZ3. M of TZ3, you cancel T inverse with T. It's S of Z3 is 0. M of TZ4 is S composed with T inverse of TZ4 is S of Z4 is infinity. Okay, so you see here this new Mobius transformation M of Z, it maps TZ2 to 1, TZ3 to 0, TZ4 to infinity. Whenever you have such property, this Mobius transformation must be the cross ratio, but with a TZ2, TZ3, and TZ4 by this condition. Right? By this one. Cool. Now let's see. Then what is MTZ1? MTZ1 by the definition is TZ1, TZ2, TZ3, TZ4. It's for all Z in C infinity. For all Z in C infinity. Then you choose TZ1 as an input. And M, remember what is M? M is S composed T inverse of TZ1. It is S of Z1. What is S of Z1? It is Z1, Z2, Z3, and Z4. Okay, so you see we get the desired equality. Right? We get what we want. And this proof does not depend on the concrete computation. It depends on the property. See it? Whenever you map a point to map 3 point to 1, 0, infinity, then that Mobius transformation must be the cross ratio. This is the property we repeatedly use. Okay. So in this construction, we always map a triple to 1, 0, infinity. We actually can construct Mobius transformation between a triple to another triple, between 3 different points to another 3 different points. And this is also unique, right? Because if you have Z2, Z3, Z4, you have W2, W3, and W4, and W2 is mapped to 1, W3 is mapped to 0, W4 is mapped to infinity. Then you can construct the Mobius transformation from Z2 to W2, Z3 to W3, and Z4 to W4. And that is unique because those two parts are both unique. Correct? Okay, so that is the proposition 3.9. If Z2, Z3, Z4 are distinct points in C infinity, are distinct points in C infinity, and W2, W3, W4 are also distinct points of C infinity. Then there is one and only one and only one Mobius transformation as such that S of Z2 is equal to W2, S of Z3 is equal to W3, and S of Z4 is equal to W4. You can consider this as a generalization of the definition, and you can also just consider it as a corollary of the definition of a cross ratio. Corollary of the cross ratio. Okay, now let's give the detailed proof. Okay, so let S of Z be the, not ST, let's use a different word, T of Z. Let T of Z be the cross ratio Z, Z2, Z3, and Z4. And M of Z to be Z, W2, W3, and W4. Okay, so this is mapped to 1, 0, infinity. This is mapped to 1, 0, infinity. Okay, then define S to be M inverse of T. M inverse of T. You see here, T has such direction. M inverse is this direction. So define S to be M inverse composed with T. Then S will map Z2 to W2, S of Z3 to W3, S Z4 to W4. Right? Okay, so this is a one, this proof part of the conclusion. There is a one, unique one. If R is another Mobius transformation with R of a Z, what letter? Zj, not use I. R of a Zj is equal to Wj. J is a 2, 3, 4. If R satisfies this property, then what we have R inverse compose S of Zj is equal to Zj. You see, S maps Z2 to W2, but the W2 is mapped back to Z2 by R inverse. for j equal to 2, 3, 4. So our inverse composed S has 3 distinct fixed points. If a Mobius transformation has 3, not 2, 3 distinct fixed points, then our inverse composed S is identity, and this implies R is equal to S. Okay, so we have only one, right? We have the only one. So whenever a Mobius transformation has more than 2 fixed points, it must be the identity. Right? It must be the identity. Okay, so far we proved the property, the mapping property from a triple to another triple, from one triple to another triple, and that can uniquely give us or can uniquely determine Mobius transformation. And in the next part, we're going to show the circle line property about the Mobius transformation. Okay, so we will continue the discussion in the next video. The lecture is not done. Okay, thank you.